This last section of the course, section 9, is about practical identification and Matlab. Here are some useful commands. You of course know the help command because you've used Matlab before. So for instance, help ARX will give you insights on how to use ARX. So before asking a question, well, have a look at this help and see if you cannot find the answer yourself. What is very important also is that you have a look at the documentation that is associated to the identification toolbox. So the getting starting sections, the user guide, and demo sections. So you type doc ident and you will see that there are quite a few examples. For instance, this glass tube process example that you can look at before you start your system identification assignment. Some people think it is a loss of time. I think it's a loss of time when you don't have a look at those sections because they give you insight, and in this way you'll start your system identification assignment in the proper way. Well, we have already seen that you can enter this polynomial a of q that is shown here in the following way. And well, you can filter a signal using a given transfer function using the command filter. So have a look at the help that is behind this command filter to see how you can use it. Well, this polynomial format and the command filter will be important for your system identification assignments. Besides working on a dataset, you will be asked to write your own ARX, for instance, function, or your own output error or RMAX function. The system identification workflow will include the following tasks. So process the data for system identification, identify the model, validate the model, and then post-process the model. And we'll have a look how you can do this in Matlab. There is one that is lacking over here, and it's really experiment design. So this is also something that should be part of this workflow, but since you will receive a data set in the system identification assignment, it will not be part of the workflow as far as this assignment is concerned. Well, the first thing that you have to do is of course process the data, and you'll have to import the data in the Matlab workspace. Well, in the easy case where you have a Matlab file, this is simply done by the load command. This will be the case in the system identification assignment, but of course in some cases you'll have the data in some other format, and so you might end up having quite a lot of work in importing this data into the workspace. As I've shown in the introductory section, please work with objects, right? Using this it data, identification data structure, using the command it data. So you can give names to your input data. You can also give units and things like that. And then when you work with this data and you do a plot, for instance, everything is done for you automatically. So please start to work with this environment from the start because it will make things easy. Well, processing the data also means selecting a subset of the data for identification and another one for validation. So in your head it might be, well, 2/3 of the data for identification and 1/3 for validation. Well, most often selecting is a bit more complicated because you have to keep in mind that you have to select data under conditions that are as close as possible to the intended use of the model. So let us use an example. You receive a data set rain river flow, and you want to use this data to identify a linear model for flood prediction. Flood prediction means level of the river is high. So in your data set, you should select data sets that are as close as possible to a near flood situation, right? So you should select data sets for identification where the river flow is high, and you should similarly select data sets for validation where the river flow is high. So it's just a bit more complicated than simply saying I'm going to split this data set 2/3, 1/3. As mentioned before, you can start by plotting the data, of course, and then have a look at, well, some first models identified using commands like impulse-est and SPA, spectral analysis, so that you have an idea of the impulse response. You can also obtain the step response. This will give you ideas about, well, the underlying dynamics, the sample period that you should use, and maybe already the model order. Okay, of course you should pre-process your data. Maybe I should put this one first. If you have missing values and outliers, you should correct for that by interpolation and use the command misdata of Matlab. In the assignment, this will not be a problem because the data have been checked and they are all okay. So what you could do also is remove offsets and linear trends so that you work around a working point. This is the command detrend, right? Remember that this is especially useful when you're working in simulation. If you're working in prediction, the influence of the detrend is rather small, right? Sometimes you want to use a filter, right? This is this LQ filter to emphasize a specific frequency region, so you can then use the command filter to filter the inputs and outputs. We've seen, and here we have already an idea of what TS should be. If you see that TS has been chosen too small and that there is a chance of oversampling, well, you should resample the data, right, using a different time interval, and you should use an appropriate function like decimate or resample that will low pass filter the data to prevent anti-aliasing before resampling, right? And to have kind of a general analysis of different features, what you can do is use the advise command in Matlab. Well, there are several commands that you can use for process identification if you're interested in a, well, spectral representation of the model, so a frequency response model. And this is a part that we have skipped here in the course. This is this section on non-parametric methods. Well, you can use the command SPA for spectral analysis, but you also have another command which is ETFE, empirical transfer function estimate. They are very closely related. It's just a question of, well, filtering between frequencies, which makes a difference. So you can have a look at that to have the frequency response of the system. You can also obtain the impulse response using a FIR model structure, and this is covered using the command impulse-est, right? And associated to that, you have a command step plot to obtain the associated step response, and then you have the command impulse plot to have an idea of the impulse response. So these are, well, two commands or two things that you can do before really starting the black box identification, where we use, well, input-output polynomial models, and we use the command, for instance, ARX output error mainly, and then possibly other commands in Matlab. You can also directly identify state space models, and this is something that you could explore using the command enforce_it, and this makes the link with the course of state space control methods. So you could then use these models to design a state space controller. And we have considered in this course that there are extensions of the ARX and output error predictor to the nonlinear framework, and for instance for the nonlinear ARX you can use this command, and this makes the link with the second part of the course that is taught by my colleague Thomas Musser. The estimation of the delay in the system is rather important because it's usually done once and for all, and when the delay has been fixed, and this is this NK, well then you can kind of choose the model structure, and when the model structure has been selected, we'll play with the parameters, for instance the NA and B and C, etc. So first method to estimate the delay is just visual inspection, and there you just need to do a plot. Very often, for instance for this rainfall river flow data, it is rather difficult to obtain the delay just by visual inspection. So what you might do then is identify the impulse response of the system and have a look at that, right? And this is using the command impulse_elst. And what you can then do is look at the values of the impulse response, and as soon as you see a value that is substantially higher than the confidence interval, well then you have identified the delay in the system. So what you could do is identify ARX models of this type, right? So NB is equal to 1 and A is equal to 0, so this means that it is also a finite impulse response model of a particular kind because it has only one parameter. And then you identify models with different D's, so these are the models that you identify, and then you can have a look at the loss function based on validation data, and where you detect an E, well this is going to be the best delay, right? An alternative to that is to identify ARX models where NK is equal to 0 and A is equal to 0. So again, this is an FIR filter, finite impulse response model, and it's of this type. So you identify the model using the command ARX, then you look at present and you check the B coefficients versus their standard deviation, and at some stage you'll see a B where the estimation, the value of the estimate will be substantially higher than the confidence interval, and this will allow you to, well, obtain the delay. Okay, and of course there is also the option for people that are a bit lazy is to use the command delay estimate. You will see that you will have to try probably a few methods and see the one that is going to give the best result. Sometimes you get even conflicting results when you use one method and another. This is because probably that your delay is, well, very close or in the middle between two values. Well, for model structure selection, work with ARX models first and try models with an increasing number of data parameters, okay, and A plus NB, and then look at the validation cost, right? This is an A plus NB. and this is your validation cost over here. And what you will see is that at some stage there will be a knee, so you have a decrease of the cost, and after a while the cost will start to increase, and it's, well, this number of parameters that you have to select, right? So there is a Matlab command that will help you, well, several, but the most important one is ARX structure, and the idea is that you can identify a whole lot of ARX model structures, for instance with an A ranging from 1 to 5 and B ranging from 1 to 5. This is possible because the ARX model, well, underlying that, underlying the estimation, you have a least squares problem. So it's first of all cheap to compute ARX models, and also you can compare them, because with an ARX model you always have the guarantee of finding the model with a cost that is in the global minimum. Okay, so comparing ARX structures makes sense from a validation point of view and from an identification point of view. Well, comparing output error model structures would not make sense, because when you identify an output error model, you do not have the guarantee that you have ended up in a global minimum. When you start comparing output error models, you might start to compare a model that has converged to the global minimum with another one that maybe has ended up in a local minimum, and that would not be very useful, right? So start with ARX models, identify a whole bunch of ARX models, and then do this and select, and this is on validation data, remember, and select the number of parameters that corresponds to a knee in that type of plot. Well, these are the Matlab commands. So what is done over here is that a data set is simulated. This is the advantage of Matlab. Of course, you can generate your own data, and of course then you know the actual system, and you can identify the model and then compare with the actual system. When you receive data from a physical system, you don't know the actual system. Okay, so there is quite a lot to be learned by simulating your own data, and have a look at what happens. So this is our actual system, okay, with the A, B, and C polynomials. We generate inputs and noise and white noise sequence. Here we assume that the input is also white noise, so that we excite all frequencies, and then we generate the data. Y is the deterministic part, B over A, and then the stochastic part. Okay, so this is the data set. We take half for estimation, half for validation, and in this case, for instance, we obtain the delay using the command delay est, right? And then we assume that D is fixed, and here you have this command ARX struct and struct, right? So this command here, struct, will allow you to identify a whole bunch of ARX models. And A goes from 2 to 5, and B from 1 to 5, and D is fixed. An alternative to fixing the delay is to use this structure, so that you obtain your delay using this ARX structure. You don't know the delay, and you say, well, it might be 1 to 5. Okay, and then you're going to identify all those combinations of ARX models and see which one is the best on validation data. Okay, so the command ARX struct uses this structure over here. You see, it uses this data set for estimation, for identification, and the other data set here for validation. Okay, so of course in here there will be identification costs that will be the smallest. Okay, either you can select this automatically and automatically select the structure that has given you the smallest loss function, right? Then you do it like this with this 0, and if you do it like this, then there is an interactive structure selection, in the sense that a window will be produced and that you will have to select yourself the structure that is used for the ARX model. So this is the window that is produced. You see here on the x-axis, this is the number of parameters. So this is really NA plus NB, and here you have the loss function. As you can see, well, you can see this knee over here. Okay, so up here we see something like that, and then you have a slight increase of the cost, right? So if you choose the automatic selection of the parameters, you'll select 8 parameters, NA plus NB, so you would have to look at NA and NB that is corresponding to that. But if you choose the interactive fashion, I would choose here to take 4 parameters, and this is what I've done over here. This corresponds to NA is equal to 2 and NB is equal to 2, and the delay was 1, right? Then what you do is click on here, you see this, and then you select and close, and this structure will be selected. Once you have selected your structure, when you run your code, you do not want to see this popping up all the time. So what you do is put the underlying code in comment, and what you do then is produce NN is equal to 2 to 1, and you use the command ARX, for instance, ARX estimation NN, right? Because you have already identified the correct model structure. This procedure of going through this window, you do it when you really want to identify the correct model structure. Once it has been identified, you do not need to go through this anymore. Well, so far we have talked about the ARX model structure that is using, well, a least squares estimation of the parameters. Depending on your needs, you can go and use other model structures, but keep in mind that these will require an iterative prediction error estimation method, and this will be the case, for instance, for output error, Armax and Box-Jenkins models. As a rule of thumb, if you're interested in prediction, then use ARX model structures, and you could complexify the model using Armax model structures. But remember that if you're using an Armax model structure, you will use non-linear least squares, and well, you end up with the risk of going to a local minimum. If you're interested in simulation, right, use output error model structures, and you could complexify to Box-Jenkins model structures. As a general rule, use as few parameters as possible, okay, and increase the model complexity if it brings a substantial decrease in the identification cost. This is because if you're using more parameters and the amount of data stays the same, well, the variance on the estimated parameters will be higher. Also, if you have a more complex model, well, the price you pay when using this model will also be higher, as we have seen previously. Well, similarly, if you decide to investigate and identify a non-linear model, always try a linear model first and see if the nonlinear model structure brings a substantial decrease in the identification cost. Okay, if the identification cost is about the same, well, there is no reason why you would select this nonlinear model structure, because the costs in using the model, either in simulation or for control, will be much higher. I will now give you a little summary on model validation. We have seen some of this stuff before, but I'll put the focus on Matlab. Well, to validate the candidate models, you should work with the validation data, and the command is compare. I've stressed the fact that this third argument, which is the prediction horizon, is very important. If you don't use this third argument, then it's automatically chosen as infinity, and this corresponds to validating the models using simulated output. So you'll put the focus on simulation. This is an error that is very often made in the system identification assignment, where we have a tendency of wanting to validate a model in prediction. So we have to use this third argument. Okay. As we have said before, it's always a good idea to compare different models in the frequency domain. So you fit an ARX model, you look at the frequency response, and you can compare this with a, well, frequency response that has been obtained directly from spectral methods. And here we have some commands, but you also have the command SPA and empirical transfer function estimate. This comes from this section that we have skipped on non-parametric methods, and where the frequency response is directly estimated from the spectrum of the output and the spectrum of the input. So to validate the models, residual analysis is a very good tool, and you should use the command resid. We'll have an example just after this slide. So what you're looking at is at the autocorrelation function of the residuals. This is the expected value of epsilon and a shifted epsilon, and then you have the cross correlation, right? This is correlating epsilon with, well, shifted versions of u. This cross correlation, well, is used to validate the input-output transfer function, and if it's not satisfactory, you should include other input terms. Yeah? And we've seen an example in the previous section where the delay was chosen wrong, and if the autocorrelation is not satisfactory, well, this means that the noise model is not validated. You should therefore adapt your model structure. If you're only interested in the input-output dynamics G, okay, this means that you're interested in simulation, then of course only look at the cross correlation function, okay, because this is the one that is going to validate the input-output dynamics. It doesn't make sense to look at the autocorrelation because this one is used for validating the noise model. And if possible, of course, always use validation data. Look at pole 0 maps using this command io pole 0 plot, IOPZ plot, and look for near pole 0 cancellations because they are a sign of over modeling. And finally, look at the standard deviations. Okay, so look at the coefficients and compare with the standard deviations, and this can be done using the command present. Okay, if the confidence interval of a parameter estimate contains 0, then you have a small estimate with a large confidence interval. Well, then you can probably remove this parameter. If all confidence intervals are large, Well, it could be that you have a model order that is much too large. Well, the validation tools that have been outlined here are very important, and I expect them in your system identification lab report. I often see a sequence of models that have been identified without any validation. This is not really a good job. I expect you to do a good job and to have model validation prominent in your report. Well, in order to illustrate model validation, what we'll do is consider an actual system, a true system, that is the one that is over here, and what we'll do is simulate it in Matlab. So obtain input output data, u of t input, y of t the outputs, and use this simulated inputs and outputs to identify the model. And then, of course, since we know the system, okay, we can have a look at the model structures that we have chosen. Are they correct, yes or no, and look at the underlying residual analysis. So this is the plan. Remember that the true system is an Rmax system, and it has, well, N is equal to 2, that's NA, 2 for NB, 2 for NC, and a delay of 1. Here in all the models, we'll assume that we know the correct delay, which is 1, as you can see, right? So what we'll do is work with 3 different model structures: an ARX model structure 2, 2, 1, an Rmax model structure 2, 2, 2, 1. So this model structure is capable of representing the actual system, okay? And then finally an output error model structure 2, 2, 1, and this type of model structure you would of course use if you're interested in simulating the system. So if you're only interested in the input output dynamics. So what you can do is identify the 3 models and then look at the residual analysis. So what we'll do here is first generate data that you can use for identification. So this is our Rmax model 221. We generate 3000 data. Here we have the actual system M that is constructed using it poly, and then you can simulate the data, and I've chosen here to use the command it input, and this is really an input here that is chosen as a random Gaussian noise. I could have used here PRBS. So this is a command that you could use later if you want to do experiment design. So be curious and go and have a look. And what is done over here is simulate the output, right? And here we have the structure construction. So we put the data in an object. Then we use a data set for estimation, half of the data, and the remaining part for validation. And what we do over here is identify an ARX model structure, an Rmax model structure, and an output error model structure, and the underlying parameters are the ones that we had decided upon before. And each time what we do is do a residual analysis, and this is really the command that will give you a plot with the autocorrelation function R epsilon and tau, and with the cross correlation function based on n data. So these examples here in the slides with code are there for your information, and please have a look at these slides before you attend the system identification laboratory. Well, remember that the true system is Rmax, right? And then it is, well, 2, 2, 2, 1, and here we have used an ARX 2, 2, 1. So this means that G can be modeled exactly, right? But that H cannot be modeled exactly. But since G and H have parameters in common, this is the AQ polynomial, well, this is going to lead in a bias of G and H. So there will be error in the estimated G and in the estimated H. This can be seen in the following correlation analysis. What you see over here is really R epsilon and tau, and this is here R epsilon U and tau. So this is the autocorrelation function based on n data, autocorrelation of the residuals, and this is the cross correlation function between the input and the residuals. Okay, this one is used to kind of validate H, and this one is used to validate G, and this is exactly what you're seeing. What I had announced is that both H and G cannot be validated using correlation analysis. So here we are in the case that the actual system is 2, 2, 2, 1, and the model that we have used is also 2, 2, 2, 1, so it can represent the actual system. So based on a certain number of data points, well, you should obtain a reasonable estimate of the actual system, and so you'll have this for both the estimated input-output model structure and for the noise model. And you see that this is indeed the case. This is the autocorrelation function, and it's validating the noise model. It is inside this confidence interval. Remember, of course, that here you expect this spike at tau is equal to 0, right? But apart from that, all lags are inside the confidence interval, so you can validate here the noise model. And what you have over here is R epsilon U n of tau, and you can see that here also for all lags except this one over here, well, you stay in the confidence interval, so with a reasonable probability you can say here that G is validated. What you will have in reality is cross correlation functions, correlograms, that do not look as nice as this one. This is because the data that you receive might have inherent non-linearities, okay, and well, you will never be able to validate either G or H with 100% probability. But what you can do is use these correlograms to kind of compare different model structures. So here the Rmax model is 2, 2, 2, 1, and here we have used an output error model structure 2, 2, 1. So this here is to model the input-output model structure, and in this case for the output error model, the chosen noise model is simply 1, right? So here you're capable of representing the actual input-output transfer function, and G and H are parameterized independently. So in this case you will be able to identify G, but obviously since you have chosen a fixed noise model, you will not be able to identify the actual noise model. And this is clearly what you see over here. So again, this is the autocorrelation function based on n data, and here clearly for a lot of lags it goes outside the confidence interval, so you cannot validate the noise model. But you don't need a correlogram to see this, because you've chosen a noise model that is 1 and fixed. When you use an output error model, you're not interested in the noise model, you're interested in the input-output dynamics. So typically for an output error model, you're interested in the input-output dynamics, so you're going to look at the second correlogram over here, and you're going to kind of discard this correlogram. And indeed, you see that in this correlogram, where you see the cross-correlation function between input and residuals, well, here for almost all lags you stay in the confidence interval, so this means that you can validate the input-output transfer function that has been identified. Well, as far as post-processing of the model is concerned, in this course we'll stick to just having a look at the individual parameters and their standard deviation using the command present. What you could do also is convert the discrete time model to continuous time models using the command D2C, and to transform, well, the format of the model, for instance, from polynomial to state space to frequency response, etc. Well, as said before, you can use Matlab's function Detrend as a pre-processing tool, and it subtracts the mean or a best fit line in a least squares sense from the data. So removing a trend from the data enables one to focus around the fluctuations of the data around this trend. In most cases there will be no trend. You will be working around 0, so that you can kind of focus on the fluctuations around the working point. Well, a linear trend typically indicates a systematic increase or decrease in the data, and a systematic shift can be, for instance, the result of sensor drift. While trends can be meaningful in some cases, some types of analysis will give you better insight if you remove the trend. And for instance, in case of a sensor drift, well, there it's very clear that you have to remove this linear trend. Removing a linear trend will also ensures that the signal becomes quasi-stationary. We've seen that from a theoretical perspective, the deterministic signals have to be quasi-stationary in the sense that, for instance, the expected value can be time varying, but it should be bounded. And a linear trend is not, or a ramp signal, for instance, is not a quasi-stationary signal. So whether it makes sense to remove the trend and use the command Detrend depends a bit on the objectives of the analysis. Typically, when you're doing simulation, or when you put the focus on simulation, it's probably a good idea to use the command Detrend. But if you put the focus on prediction, well, then detrending doesn't bring a lot. And you have to remember that if you do detrending, it comes with a computational cost when the underlying model is going to be implemented in real time, because you'll have to detrend the data that you feed to the model, okay? And then, well, when you look at the output, you'll have to correct this and bring everything back to the correct operating point, and this is of course computationally expensive. So a good example to explain detrending is the following. Once assume that you have a data set where input is, for instance, cloudiness or solar spots that you have on the sun, and the output is the average temperature on Earth, for instance. Well, if you would look at the output temperature, you would observe a trend, and this is because of the global warming effects of the last 50 years. And of course this trend has nothing to do with the input, which is cloudiness or the number of solar spots on the sun. So clearly here it's a good idea to use the command detrend to remove this linear trend, as it has nothing to do with the input. Of course, if you're interested in the output average temperature, what you will have to do is use your model, okay, and the output will be the variation around this linear trend, okay. So you'll have to add the linear trend at the output of the model. So what we do over here is simulate a stock price, so the price of a given share, and we simulate it as a linear trend, right? And the other part, we take it as normal data, where we take the cumulated sum. This is sometimes called a random walk. Okay, so you'll have a look at this data and you'll clearly see the linear trend. So the command detrend is used to obtain the detrended data, and of course what you can obtain is also the trend. You simply take the original data and you remove the detrended data, and then you can have a look at this in a plot. So here in blue you have the original data that has been generated, right? This is this linear trend plus this random walk around it, and then what is done is, well, the command detrend is used, and the detrended data is used here below in pink. And what you see here is of course only the random walk, so the variation around 0. If you're interested in the trend, well, you take the difference between what you have here in blue and what you have in pink, and this will yield the linear trend. So for modeling purposes you would use this one, and the output of the predictor would be, well, the variation that you have around the linear trend. So to construct the overall prediction, you would have to take the output of your prediction model and add the linear trend. Well, in this last subsection of the course we talk about oversampling, and this is really a phenomenon that appears if TS is chosen much too small, right? And in this case this might lead to this oversampling phenomenon. We have already seen one of the indicators, and it's probably not the easiest one, and well, it consists in looking at the input-output dynamics, have an idea of the bandwidth of the system, and then look at the noise model. And if you see high frequency disturbances, well, above the bandwidth of the input-output system, well, it's a sign of oversampling, and then you should decimate your data. Remember that decimating the data is, well, changing the sampling frequency. So you should first use a digital low pass filter to prevent aliasing, right? And then picking every est data point. This example here of high frequency disturbances is very well explained in this example that you can run using docident, this process of the glass tube production. Well, if TS, the sampling period, is chosen too small, it's quite easy to come up with a predictor. Since TS is small with respect to the main time constant of the system, from one sample instant to another, nothing really has happened in the system. This explains why the naive one step ahead predictor, which consists in saying I'm going to predict my value at time t uniquely based on the previous measurement, will be a good predictor. Okay, Well, basically the underlying models, okay, will not have captured the actual dynamics, and this explains why the simulation fits will be really bad, right? So there will be a big difference between prediction and simulation fits, and this is a clear sign of oversampling. You can see here from this naive predictor that the underlying models will have pole clusters around the unit circle. So if you see this, this is also a clear indication of oversampling, and you can see, of course, all this using this command IOPZplot, right? So the predictor does not capture the dynamics, and the corresponding simulator tends to give very bad results. The predictor does not capture the dynamics, of course, except if you choose unreasonably high model structures. Okay, so this is another way to see this. If you have to use model structures with a high number of parameters to have good simulation results, this is again a sign of oversampling. So it could very well happen that you have started the identification exercise and that you have had these problems that are described over here, and that you suddenly realize that your data set is such that TS is too small and that you have an oversampling process. This is again showing that the identification process is iterative. But of course what you should do is make it a habit in estimating the step response or the impulse response of the system. And as a rule of thumb, if you have access to this estimated step response, for instance, then, as we have seen in the course of digital control, there should approximately be 10 to 15 samples per rising time of the step response. If you use the impulse response as a rule of thumb, there should be 3 to 5 samples per rising time. Okay, so make it a habit to first identify either the impulse or step response, check if your TS is correct, right? And if not, well, you'll have to decimate the data. Of course, it would even be better to do a test on the actual system and estimate TS. Of course, if you're in an industrial environment, then you'll use the step response, and based on this step response, you'll be able to choose your TS during the experiment design. Well, in general, you'll have the presence of several of the previous indicators, and this will allow you to conclude if the data has been oversampled or not. So in your lab report, I would like you to really motivate if the data is oversampled or not. If you come to the conclusion that the data is oversampled, you should use the command decimate and or the command it resample. This is another one that resamples the data, but after low pass filtering to prevent anti-aliasing. So never pick every end sample without the appropriate low pass filtering, otherwise you'll have frequency folding effects, and this will be illustrated next. So again, what we'll do is use some Matlab code to illustrate what I'm trying to show you. So here in the background there is a TS that we assume to be 1 second, right? So the sampling frequency is 1 Hertz, so that the Nyquist frequency will be 0.5 Hertz, right? So what we do here is really generate a time series. So we have only an output and we generate it as a ARMA model. So you have C over A and you have a white noise that goes through this transfer function, right? And then we have the output, and we use here again this identification toolbox structure that you can use for identification. So we have three spectra of the output, three spectra that are going to be computed. The original spectrum is going to be computed using this command over here. Remember, SPA stands for spectral analysis. Then we'll do the spectral analysis, but on the data where you have, well, picked every decimal points. And as you can see, there has been no low pass filtering. So here you can expect, well, aliasing, right? So here we do the resampling or the decimation in the proper way in this function. Before taking every decimal points, there is a low pass filtering that removes everything that is above the new Nyquist frequency. As you can see here, the decimation factor is 4. Okay, and then what we do here is take these three spectra and have a look. We compare the original spectrum with the case where we do not do this low pass filtering, and then we compare the original data with the case where you do the resampling in the proper way. So what you can see here in blue is the spectrum of the original output signal. Remember that we had used TS is equal to 1, and indeed you can see here that the Nyquist frequency is 0.5 Hertz. So what we see here is the spectrum in green of the data that has been obtained by taking every 4 points without applying a low pass filter. Since we take every 4 points, now we have changed the Nyquist frequency and it has been divided by 4. So here we have 0.25 Hertz. This is the new Nyquist frequency, and as you can see here, the spectrum of this signal that we have generated by picking every 4 points, does not correspond to the original spectrum, and this is because, well, we have problems with the sampling theorem. We should have removed every frequency above this new Nyquist frequency before changing the sampling frequency. So this is really not the way you should do it. So here again you see in blue the spectrum of the original signal with a Nyquist frequency of 0.5. We resample the data, so with a decimation factor of 4, so the new Nyquist frequency is divided by 4, and in this case here we have done a low pass filtering before taking every 4 points. Okay, and you can see here that you have a good fit and that the spectrum corresponds to the spectrum in blue, except over here, and this is because, well, the low pass filter, in order to remove everything that is above the Nyquist frequency, starts to act a little bit before the Nyquist frequency, so that you have enough attenuation at the Nyquist frequency. So this is really the way to go. Use the command resample to resample your data, because in the background there is this anti-aliasing filter acting. So here you have an example of rainfall river flow data, and you'll probably have some data set that is also going to be used for flood detection in your laboratory assignment associated to this course. So here the rainfall is the input and the river flow is the output. And what is done here, you see here in blue, right? This is the original river flow. And in the data sets, very often there is also oversampling, right? You'll have to determine the decimation factor. And what you can do then is, of course, decimate the data. And what you can see in orange here is the decimated river flow using the resample command. So here it's simply done using a resample. And of course, since you have low pass filtering, there is a kind of a lag that is showing over here. For the rainfall data, what you see here again is the original data. It's, well, the rainfall in an hour, right? And what you see here in orange and red is decimation, right? So it's kind of data that has been decimated to n hours instead of having hourly rainfall. Okay, in orange what you can see here is decimation using the resample function. And what you can see over here is after resampling, using this resampling command, the rainfall becomes negative. Okay, so this is really counterintuitive. So in this case we would like, well, not to use this decimation by resampling. So what you can do is really compute the average rainfall over n hours. So you can do this by summing the rain that is falling and then dividing by the number of hours. So we can have a look at that by zooming on the data. And you can see that indeed, well, using resample, the rain becomes negative, and this is the result that you have with this averaging of the rain over n hours. And you can see that this delay that you have with the resampling in the river flow, you also have it, of course, on the input data. So if you're working on this rainfall river flow data, you can use the resample function of Matlab for the river flow, but you should use your own little function that decimates the data by averaging out the rainfall over n hours, where n is the decimation factor. Well, you might wonder if averaging out the rainfall over n hours is the good way to go. Is this not going to generate aliasing? Well, part of the answer is that, of course, if you're averaging out, well, averaging is kind of low pass filtering. So you have here a filter that will remove the high frequency components above the new Nyquist frequency. If you want to investigate this further, what you can do is, well, compute the spectrum of the original rainfall and then have a look at the spectrum of the rainfall after decimation with this averaging procedure, and over the new frequency band 0 to the new Nyquist frequency, this should correspond. Well, this concludes this course on system identification and linear theory. I hope you liked it. Do not hesitate to react. If you see typos, if you think of improvements and things like that, you can see my email address, so preferably react by email. Thank you very much.